Welcome to the SAFO seminar series for the fall semester. And today I'm very happy we have Dr. Larry Burke from PNNL and to come here to kick off our seminar series for the new semester. Okay. And Dr. Burke is the director of the division of atmospheric climate and earth sciences at the PNNL. And that is a large division. It has 140 staff and support the staff members and technical and support staff members. And their research budget is $36 million per year. And so that is, to give you an idea, SAFO research expenditure in the past few years is $6 million something. But the last year we got awarded $9.6 million for that. Yeah. So, good job, everyone. Yeah. But what Dr. Burke is doing, managing is much larger portfolio. Okay. And so really that is a lot of responsibilities. And Dr. Burke has been in charge of large initiatives. And today he will talk one of the centers he led for that. Well, Dr. Burke, he got his undergraduate degree from Pennsylvania State University in meteorology, and that is really the top place for studying meteorology. And a lot of people I saw in that area, then when we trace their back, their education background is always at the Penn State meteorology. And then he got his PhD from University of British Columbia, that is in Vancouver. And then had a very successful career, in both research and administrations and at National Lab, DOE. And also I'm grateful for Dr. Burke to come here to talk to our students over the lunch about, different things you are interested in. And for those of you who didn't get a slot for lunch meeting, feel free to ask questions after the seminar. Well, without much ado, let me turn this to Dr. Burke to his talk.
Right. Thank you very much. Yeah, thanks. And so it's great to be here. This is a wonderful space. I'm happy to hear when you remodeled the building that you left this room as it is. I think it's pretty cool. So it's great to be able to present here. And I struggled a little bit just trying to figure out what exactly I wanted to present. My background clearly is within atmospheric science. We're in an engineering department, so I tried to think of some things that I thought would be interesting across a fairly large cross-section of the scientific. Got the lights? Audio is good? Okay. So I will dive in. I do want to point out my co-authors. I'm at a point in my career where I'm largely presenting the work of others. And so if I say something stupid, it's probably because I didn't understand it when they explained it to me. If it's something that's really cool and great, I tried to stay out of the way. Right, so just some topics for today's discussion. I thought it'd be useful to talk a little bit and provide an introduction to the Department of Energy National Laboratories, of which PNNL is one, and then spend some time talking about atmospheric research at PNNL. And then the meat of the talk is really going to be focused on our floating wind Earthshot, challenges in energy floating wind in a changing climate. You can guess by that title why it is not so popular with the current administration. If there are naughty words, I think I've gotten 3 or 4 of them within that title, right? But really focusing on simulating operating conditions for floating wind turbines. And then if we have time, some application of AI for downscaling relatively coarse Metocean simulations. And then the last slide is just a few ways that you could maybe think about working with PNNL. So there are actually 17 Department of Energy national laboratories scattered across the country. Pacific Northwest National Laboratory is the biggest circle, only because I'm the one giving the talk. Not because that lab is particularly larger than any of the others, but it gives you an idea of where they are scattered around the country. They have different foci. and some of them you may be more familiar with. Lawrence Livermore, Sandia, Los Alamos, the so-called weapons labs that were really responsible for developing nuclear weapons, Savannah River, and PNL and Oak Ridge, which were really associated with production of nuclear material, but they all trace their roots back some distance in time. Our missions, of course, have diversified, and this is just to give you a flavor about PNL. There's a lot of numbers there, but I think I want to highlight in the center, right? Scenic Richland, Washington, and we get about 7 inches of rain a year, so it's actually quite dry. The sagebrush gets lush at certain times, but we also have an office, interesting enough, in Washington, D.C. The Joint Global Change Research Institute is actually a collaboration between the University of Maryland and PNL. So you can go to the University of Maryland campus. If you know where to look, you can walk into the office building and it says PNL. And then we have an office in Seattle. Most of our oceanographers are based there. We have a marine sciences laboratory in Sequim, which is probably most like the facility here. I think it's probably not as cool because the river doesn't actually flow through the building. But they are able to actually pull water from outside the bay for the research that they do there. And then a relatively small group of people in Portland, Oregon, really, they initially were put there to focus their attention on Bonneville Power. I think the main thing is currently we're about 6,000 employees. That's today, tomorrow, who knows? Right? Exactly what the future may hold. And then the lab as a total had over 1,600 peer-reviewed publications last year. Our division is really focused on expanding the knowledge of fundamental atmospheric processes, developing modeling capabilities, and improving the understanding of how human and natural systems interact. As Liam mentioned, we have about 140 staff and postdocs. This is a picture that we took 2 years ago. We actually had a day and a half an event where we brought everybody back. We have probably 25 to 30 staff who are virtual. And so we did an event back on our main campus. This is just a group photo taken associated with that. And our backgrounds include atmospheric science, chemistry, engineering, and data science. In terms of DOE's role in the science, there's really contributions to atmospheric measurements. And these, of course, are very critical, but sparse, relatively sparse and infrequent. So you can think of surface networks. Most of these are measurements within about 10 meters of the surface. So measurements at airports, air quality networks, state-run mesonets. There's a small smattering of towers. I mean, one of them is similar to the wind tower, or tall tower here at University of Minnesota, close to the wind turbine. Satellites, of course, are space-based remote sensors that provide measurements of many atmospheric properties. But where do we see, and whether radar, so precipitation measurements using kind of the standard suite of operational radars. But what is the Department of Energy's role in all of this? There is the Atmospheric Radiation Measurement User Facility. And this is really the world's, I think, and I'm probably a little biased, the world's premier ground-based observing facility advancing atmospheric science. It is a DOE user facility. You can go to their website. You can download the data. It's completely free of charge. There's data products there. I would encourage you to go check it out if it fits your research. If you have questions about it, reach out to me. I can get you in touch with the right people. There are 3 permanent fixed sites, one on the North Slope of Alaska, one at the Southern Great Plains in Oklahoma, and they're just setting up a new one in Alabama. And so I've been talking with some people that have been doing some work at the Alabama field site. Also a site in the Azores. We'll see how long that one actually stays in place. And then they have 2 what they call mobile facilities. By mobile, right, they're actually 4 or 5 sea-tainers. So they tend to get deployed for a year or 2 at specific locations, but those deployments are actually proposal-driven. So people in the community would write a proposal to deploy that instrumentation, and they have some airborne assets as well. In addition, there's the Wind Energy Technology Office, which I believe still exists. And there we have a series of land-based and offshore measurements, so the weather forecast improvement projects, Awaken, which is a field study looking at wind turbine wakes, and we have a LiDAR buoy program. So we have a small fleet of these buoys. The main instrument on it is actually a Doppler LiDAR. So it's measuring wind profiles of wind speed and wind direction from the ocean surface up to about 200 meters. You can also see that there's an eddy covariance system here on the front, so we can measure fluxes near the sea surface, and then some other ancillary measurements on board as well. But I point out here that these are critical in space are critical, but relatively sparse and infrequent. So of course, models become a very useful tool to also increase our scientific understanding. The top panel here is some recent simulations using the Energy Exascale Earth System model, or E3SM. This is kind of DOE's flagship model. This is being run globally, in this example at 3-kilometer horizontal grid spacing. So this is for a global Earth system model. This is incredibly high resolution. And so you can see an awful lot of detail on some of the flow features. It's basically, I think, total water vapor that's being displayed there, but a lot of the details of this planetary circulation. This is very computationally expensive. They can't do it for true climate simulations where you have to simulate a couple hundred years, but it is a valuable tool that they can run for a year or two simulation period. And then we are also, of course, doing quite a bit of, ooh, that's not what I wanted to do. It should. These clouds should start moving, but they are not doing that. We'll let it go. It's not that critical. But we're also doing some work with large eddy simulations, some of which I'll show later today. This particular example is shown with a new LES code that's actually written in Python. And so it's something that we hope will be much easier to port to GPUs than some of the existing large eddy simulations. And of course, we do many of our simulations on the Department of Energy's compute clusters. So now we're going to drill down a little bit into the actual science part of the talk. And really the idea here with our floating wind in a changing climate was looking at trying to reduce the cost of floating offshore wind energy to get it to the point that it's cost competitive with other forms of energy and becomes a viable resource. You might guess with floating wind, changing climate, this is part of the reason that the deck was kind of stacked against us, in addition to being a Biden administration priority. But the goal really was to support a diversified energy portfolio by reducing electricity costs and improving the grid reliability of offshore floating wind farms. So really it's about pulling together a really broad group of scientists. And so we really wanted to leverage multidisciplinary, multi-institutional teams and use existing Department of Energy models so you can get a flavor of the team there. So from across a wide range of Department of Energy labs, university collaborators, and NCAR. So we envisioned it really with 4 different themes. So we have a Metocean theme that's really looking at the Metocean conditions, the operating environment in which the wind turbines would work. A turbine and farm theme where we think about how do we best control a floating offshore wind turbine? What technologies do we need? How do we optimize that control? Because we could optimize for things like power production, but maybe in this particular environment, it makes more sense to optimize the controls for reliability. Then we can provide a time series of wind power to our grid theme, who would look at how do we actually integrate this power onto the grid, right? Because it really takes this whole system to get us an idea of where the cost points, the high cost points are in the floating offshore wind environment. I point out, too, using existing Department of Energy models, and part of the challenge is each one of these themes has essentially an exascale model behind it, right? So it becomes very computationally expensive to do simulations across this entire operating environment. And so what we had envisioned, and we weren't able to see that to fruition because of the ending of the project, really was something we were calling a digital energy system. So using machine learning to help tie these different approaches together. We had a very diverse leadership team with a wide-ranging expertise and experience. So we had 2 people from each of these science themes. In each case, we tried to have someone a little more senior and someone who is maybe not early career, but at least a little bit not as well seasoned as some of the others. But I'm really quite proud of the diversity of that team, and I think we did a great job coming together. We ended up really only having about 2 years of the project. And as you might guess, with these different disciplines, it takes quite a bit of time just to get to the point where you can understand each other. And I felt like we were just kind of getting to that point when the funding was decreased some. But we won't dwell too much on that in the context of this talk. And here I'm going to focus, I talked about the wide range of activities that we have, but here I'm really going to focus on the Metocean part, because I thought that was probably most relevant. It's the part that I'm personally most familiar with, so it's a little bit easier to talk about. And what's important for floating offshore wind energy. Now, at the most basic level, right, the winds are the fuel for the wind farm. If the wind doesn't blow, the turbines don't spin and you don't get any power. But we're also interested in wind waves and currents. And these are really important for the design and operation of the floating wind turbines. One thing that was fun to learn about today was some of the work with breaking waves that's being done here. That's really something we didn't anticipate being able to consider, but I think it also has important applications for stresses on the structure. Within this Metocean theme, we had 3 different science questions. I'm not going to go through these in great detail, but we wanted to think about how wake parameterization, so understanding wind farm wakes, how a downwind turbine might be affected by something upwind. This is collaborative work we were doing with Julie Lundquist at Johns Hopkins. The impact of large-scale processes and improvement on subseasonal to seasonal prediction. So there we didn't actually say climate, but really helping us understand the wind resource and how that might change in the relatively near future and what sort of predictability we might have. And then the impact of coastal processes, because we know that these machines might not be that far from the coast, and how those coastal processes might impact wind power production and energy cost. With that in mind, we actually have a suite of atmospheric models or coupled models that we're using. At the very left is E3SM. So this is the energy exascale model that I mentioned before. It's a global model, but it does allow us to zoom in on particular regions, and so we can zoom in on the West Coast. And then some coupled simulations using WRF, ROMS, and WaveWatch 3, so a regional scale model. And then large eddy simulation that we would ultimately use to help us understand some of the details of flow around the wind turbines. Within this particular project, we focused just on the West Coast. This was largely a budget move, and recognizing that the water depths on the West Coast are deeper, we're more likely to see deployment of floating wind turbines there. The FlowMass project that Liam was involved with, I think, has both East and West Coast components to it. So they were, I think, a little bit braver than we were in that context. And we know that there are actually a wide range of science questions that are important for floating wind energy or offshore wind energy in general. And Will Shaw had a paper that came out in 2022 in Wind Energy Science that highlights what some of those science questions are. And then these are just some cartoon kind of sketches showing a wind turbine in the various aspects of the planetary boundary layer, where we would have a wave boundary layer, a surface layer, and then a much deeper atmospheric boundary layer with a free troposphere. In the case of a convective boundary layer, that might be a kilometer or two above the surface, whereas in the stable boundary layer, it might be quite close to the surface. And this has important implications, particularly as we think about floating wind turbines off the West Coast, where we tend to have relatively shallow stratocumulus layers, that you could actually have the tops of the blades coming out of the atmospheric boundary layer into the free troposphere through the top of the cloud field. So you could imagine that these added amounts of turbulence could have an important impact on the clouds that exist in those regions. But some science questions that we wanted to investigate. We understand that the marine atmospheric boundary layer is poorly observed. We believe that air-sea interactions impact the operating environment. The coastal boundary generates atmospheric phenomena important for wind generation. And that the optimal modeling approach in many of these cases is actually not clear. So we're going to I would like to dive a little bit more into the wind wave coupling. And I know that there's people here in the audience that are probably more experts in this than I am. But certainly there's a number of different approaches we can take. There's the conventional distributed roughness approaches. So these are a Z-naught and a Carnot relation. This is what's typically used in mesoscale models of the atmosphere. But we know we want to capture some of the dynamic changes of the sea surface, and we want to be able to resolve some of these interactions at fine scales. So this Charnock approach is really just a phase wave average. We just apply an equivalent roughness length, similar to what we would do for Z-naught over the land. It's commonly used, fast, relatively easy, and can make use of a wave model. So we actually have done some work trying to couple this with WaveWatch 3. So we do have some wave information feeding in for that estimate of Z-naught, but no interaction other than that. There is a two-phase approach, and in our case, this was led by Humberto Cerde at University of Puerto Rico. And so this is the explicit representation of wind and waves. Hopefully here we have a more accurate representation of wind-wave interactions, but it has a relatively high computational cost because we have to model the interface of the air and water. And then a third approach that we're calling moving surface drag, or MOSD, and this is where we include a representation of a wave phase. It assumes ideal flow over a logically piecewise representation of the waves. So this is work that Charles Menevue at Johns Hopkins is leading. So we're going to start with Umberto's work, because I think in some ways it's the most faithful representation of the physics. So I thought it was best to start with that, and then we can move to some of the approaches that require a little more simplification. And in this case, we just have a domain that contains air and water. It's really one fluid with spatially varying properties. And so we can define a distance function for each point in our grid that really allows us to distinguish between air and water. And then we have a transport equation to track the sea surface evolution with time. And then we use a fairly simple representation in the ocean. In this case, this just gives you an idea of the computational domain. The Ds are just a representation of how many wind turbine diameters there are. The simulations that Umberto did include 3 wind turbines, and we also assume neutral conditions and a relatively moderate wind speed of 8 meters per second, which is what we call region 2 of the wind turbine. So it's where the power generated is varying very quickly with the actual velocity. And we can imagine kind of some extreme cases, and we also discussed this in one of the group meetings earlier today, that we're just looking at a lined wave case where the wind and waves are perfectly aligned, and then an opposing wave case where they're going in actually directly opposite directions. And looking at how that might impact the velocity profile. Raghu, Krishnamurthy, and I had some discussion about the accuracy of these particular figures, so don't get too hung up on the exact details of the wind profile, only that we would expect the wind profile might be different when the wind and waves are aligned to when it isn't. And then we tend to define things so we have a wave velocity and then the air velocity at 10 meters over the surface. And here we are looking at some cases that Umberto has run over a relatively small value of the CP over U10. Leanne gave me a comment at AGU that we should look at a wider range of values. I provided that feedback, and this is what we have. But recognize that it's over a fairly narrow range of this wave speed divided by the air speed. In this case, showing just 3 different wave fields, but he ended up running 5 different cases. Yeah, okay, everything starts, that's good. So these are some examples that Umberto ran. The top panel is the vorticity magnitude, so you can really see the blade tip vortice along the top. You can see the turbulence near the surface. In the opposite direction, right, there's certainly more red closer to the surface than we see in the along wind direction. And then if we look at the streamwise velocity, you can clearly see the wind turbine wake in each case, but significant differences in the turbulence relatively close to the surface. I'm going to take a drink and let you just absorb them. So there's clearly some differences in the operating environment for the wind turbine for these 2 extremes. We can look at the evolution of the wind farm wake, and these plots just show the velocity as a function of the upstream velocity, so they start at 1 at various distances within the domain. And so in the top panel where we have the along wind, you can see there's actually not much difference in those 3 different wave fields in terms of the wake recovery, how long it takes the wake to get closer to the U infinity value. If we look at the case with the opposite winds, and we can see there that the red and green lines are actually recovering a little bit faster. So as the A value gets larger, as the value of A or the CP over U10 gets larger, that we see a little bit faster recovery in the wind stream wake. So this is important as we want to understand how far apart we would actually want the wind turbines to be. We can look at normalized power. So similar plot in a sense to before. The blue are where the wind and waves are aligned. The red is when they're in opposite directions. And as you might have guessed from the movies that I showed, the wake is recovering a little bit faster when the wave and wind are misaligned. And so we see slightly higher or a little bit larger power. I do want to state that this figure is maybe a little bit misleading because the normalized power range is actually pretty small that is shown there in the figure. And then we also see some differences in the power fluctuation. So one of the things we're interested in is how much the power might fluctuate over a period of time as a function of these different orientations of the wind waves and the turbine, how deep the turbine is into the array. And we can see that for the aligned case, we actually see the largest difference at turbine 3. For the opposed cases, we see the largest difference in the variation in power at turbines 1 and 2. We're not entirely sure why that's the case. That's something that we'll be looking, or if we find resources, we will look into in a little more detail. So now changing to a little bit different treatment of the wind wave coupling, and this is work that Charles has been leading. Many of you, I'm sure, are familiar with the Let's Go flow solver. There's an example from an earlier paper. So starting off with the Navier-Stokes equations, these are should be relatively familiar to folks, especially for neutral flow. We can apply an actuator disk model, and so this is treating the spinning wind turbine really just as a disk, a drag force within the flow, and some of the consideration in terms that we need to think about in the context of that, and adding the fact that the turbine can now move, right? So it's a floating wind turbine, it's able to move in the flow. So we end up with a drag force on the body frame. Again, thinking about things in the region 2 of the power curve. Relative velocity in that global frame. Then we want the relative disk average velocity. This is a number of steps here. And then ultimately, we end up with a drag force per unit volume, and then we can insert that back up into our governing equation for the flow. And then we have a simplified platform motion representation. So this is the wind turbine. The IEA 15 megawatt reference turbine, so it has a diameter of 240 meters and a hub height of 150 meters. And based on the University of Maine semi-submersible platform, we assume a length scale of the platform of 90 meters. This is really just the platform that we decided to use in the context of this project. The goal really was not to spend much time and energy on the details of the platform, but we took something that is standard is a strong word, but it's certainly a proposed platform that could be used. And then approximate a 2-point difference as the platform moves back and forth in the waves. And so we get a very complicated equation that includes the pitching amplitude that's a function of the wavelength, the length scale of the wind turbine, the wave steepness. And so we make some assumptions just so we're able to actually complete the calculations. So thinking about the wave representation, so we have this moving surface drag. So we end up with two different terms that we're using in the surface drag. The EQM term is really looking at the unresolved small scale features of the air-sea interface. And then the WPM is how we actually account for the term accounting for the waves. So we can define those, and these are all equations that have appeared in an earlier paper. And so we really determine the pressure drag from ideal potential flow. And then we also think about the effect of unresolved ripples and viscosity, and that's really modeled as a Z0 approach. So we end up with the C, which is the wave speed, U, which is the air speed, the undulating surface, which is moving our wind turbine around. And then we compare that to a traditional equilibrium wall model. And just including the equation for completeness. It won't be on the exam. And so taking a look at this domain, so we end up with about a 5 by 2.5 kilometer domain, about 700 meters tall. 210 by 100 grid points. In this case, we're deploying all of 6 wind turbines. And so to give you an idea of our boundary conditions, we have periodic boundary conditions in the streamwise and spanwise, free shear at the top, and then we provide a pressure gradient force. And then for the bottom surface, we have the MOSD plus ripples, and then we compute that to the EQWM approach. And then we look at several different cases here because depending on the wavelength and the spacing of the waves, things are moving either in phase or out of phase. So we have the fixed bottom case, and this is just, as you might guess, what happens when the wind turbine actually doesn't move relative to the waves. We have the in phase case where we see the wind turbines rocking in sync with each other. Then we have an opposite phase where the wavelength is just such that the first two move together and the middle one is kind of the outlier. And then there's an incommensurate phase, and this is Charles' word, not mine. I would have picked one that was a little bit easier to remember as I go through the details of the talk, where they're kind of moving just all willy-nilly. Right, so we can look at how these differences might impact some of the details of the flow. And so this just shows a time height cross-section looking at the streamwise velocity through one of the rows of turbines. So the fixed bottom, in phase, opposite phase, and commensurate. As I was looking through this, I kept trying to see if I could notice anything different. And one of the things that really struck me was if I had not labeled it, I think it would be really hard to guess which panel is which case, right? That the flow is turbulent and the motions are relatively small enough that it's hard to see just by eye in a figure like this, much signal, but it is pretty mesmerizing. So it's a little bit like a lava lamp, I think. We can also look at an XY plane, so looking at a projection through the wind turbines, and there again you can see the wakes. And I also think the same as before, it would be hard just to the naked eye looking at these to say, oh yes, this is the panel for the in phase, this is the panel for the opposite phase. But still kind of mesmerizing. So if we don't see kind of the smoking gun, so to say, here, then we know we need to dig down and look at things in a little bit more detail. And that is what the team has done. So here we're showing average velocity, average U component of the velocity as a function of height. The EQWM shows, well, both cases really show a double law structure, where at relatively high heights, we have one fit, and then a different fit at relatively low heights. And this is reproduced in both. But the MOSD shows different profiles for different turbine pitching and wave motion. So the panel on the left, those colored lines, which represent the different orientation of the different orientation of the wind turbines relative to each other, do show differences. And so while we didn't see differences when we just looked at those time series, we do see some differences here in the average as we look aggregate over a much longer time period. And the idea is that here that the EQWM shows negligible variance across the cases, making us think that the MOSD is actually more appropriate and more useful for some of the simulations that we're doing. So we can do some additional analysis. This is actually showing the time average or the time evolution of the wind speed for the fixed, opposite phase, in phase, and incommensurate. And one of the things that's really noticeable here is how much variability there is once we add the motion of the platform. And so these little, Charles and I had a discussion about this, that's not an envelope of values or something like that. That's actually oscillations in the wind speed as a function, small oscillations in wind speed as a function of the tower moving. And the region 2 area where we expect to see the nonlinear relationship between the wind speed and the power is highlighted in the red bars. If we take a look at the power, and this is just a numerical calculation of the power from the relationship shown up above, so it's not necessarily what you would see, right? There's no control strategy of the wind turbine. certainly differences in the power as a function of being in phase, opposite phase, or incommensurate. And it gives you an idea of what some of the challenges might be if you were trying to design a control system for your wind turbine in these particular kind of environments. And then we can roll things up yet another level and just look at some of the mean disk velocities and the mean turbine power in each of the case. So if we look at the fixed base, we have a mean disk velocity of around 6 meters per second and a mean turbine power of around 9 megawatts. For the other cases, we see some increases. I guess for the in phase, it's actually a slight decrease in the velocity, but an increase in the power. And then the opposite phase and the incommensurate phase, some increases as well. And some of this is just as the wind turbine is moving, because of the nonlinearity in that transfer function, the increases in speed have a greater impact on the power than the decreases. So the main result here is really that the relative phases matter in terms of the amount of power that's generated. And then I just have some figures here highlighting some of the variability and how the variability increases as we go from the fixed bottom on the left for the velocities and the pitching angle, and then ultimately how the mean turbine power increases. The 2 bars here are just instances where the wave amplitude was held at 3 meters and a pitching angle and an extreme pitching angle was assumed. In reality, the wave amplitude of 3 meters was specified, and the pitching angle could change some. But this is really just designed to give an idea of the range of results, or kind of a sensitivity to these 2 parameters in the context of this study. So moving upscale even further, we wanted to do some longer term simulations, so some mesoscale simulations, something that we could use as input for some of the other modeling studies that we were doing. Excuse me. And this is work that we did using WRF, the Weather Research and Forecasting Model, WaveWatch 3, and the Regional Ocean Modeling System coupled together. So really giving us a system that we could do the ocean, waves, and meteorological conditions down to about 1 kilometer scale. And really what we had envisioned here was looking at some of the events that we think would be important. So in the top panel, that's just an example of observed low-level jet cores at Merrill Bay. So this is actually data collected from our floating Doppler LiDAR in that region. And you can see the number of occurrences. And I think this is, I believe it may be over 2 years, the number of low-level jets at the bay. And so certainly you can see that our wind turbines would be operating within a region where we would expect to see some significant low-level jets that could have important impacts on both the resource as well as wear and tear on the machine. We also wanted to make sure we could do our simulations over a range of different atmospheric events. So things like atmospheric rivers, where we have large transport of moisture to the West Coast, heat waves that might be important, both in the ocean and the atmosphere, and the low-level jet cases. And I think what's important too, from a meteorological standpoint, is really how do we convey the information about the variability. And the panel on the right is just a time series of on the top, of wind speed at a site in Oregon, relatively close to our lab. The black line is the observed wind speed on a tall tower. The gray lines are actually an ensemble of about 100 different WRF simulations. And you can see, I look at that and I say, hey, that wind speed looks pretty good. The bottom line is the wind power calculated from that same time series. And so you end up with these crazy periods. Let me see if I can. Like in here, where the wind speed or the wind power is ranging from about rated, which is about 1.6 megawatts, down to 0.4 megawatts, right? And these are just based on the spread of the meteorological meteorological model. So thinking about how do we communicate this kind of variability and the impact of that variability downstream on the grid? And then finally, to wrap up, we were interested in different ways to downscale relatively coarse simulations. So in this case, we're using machine learning really to deliver accurate and fast wind simulations. So in this case, we're using a language-inspired super resolution architecture, or LISA. So it's really based on some of the same ideas as the large language models, but applying them to a different space. So really using a transformer-based architecture, which we think is better at finding long-range dependencies and complex relationships. It has some additional flexibility, and we think it's better suited to capture some of the complex events that we were seeing. And in this case, we started with ERA 5, used NOAA's high-resolution rapid refresh model as the training data, and used this to help us go through this encoder-decoder combination to come up with higher resolution output. And so what we see here, these are just maps of the correlation between her and then the machine learning derived approach. And so we get relatively high correlations, particularly as we move away from the coast. And then our accuracy is really just looking at how well the LISA model reproduces the right categories of wind speeds. So are we above or below the cut-in speed? Are we in the rated area, or are we beyond the point where the machine would shut down? And so that's just the measurement of accuracy that we're using in that particular case. And then looking at 3 different kinds of events. So here we have an atmospheric river, a low-level jet, and a downslope wind. So looking at winds coming off the coast. The red line is the HER, so essentially our observations in this case. The blue dashed line is the LISA model, and then the dotted line is UNet, which is a more standard way, a standard machine learning application. And we can see that in general, the LISA approach is doing a better job in terms of the bias, and I think even just kind of eyeballing it, looking at some of the variability in the HER. So we're reasonably excited about this particular performance. So to wrap up, the kind of the sciencey part of the work, I gave you an overview of DOE's National Laboratory System. Talked some about ACE-WIC, which was designed to bring together a multidisciplinary team to solve complex challenges. And then a little bit of some of the results that we have. So 2 new approaches to more accurately account for wind wave coupling, really with the ultimate goal of informing control strategies. Accounting for wind wave interaction can be important for estimates of power. And then various AI/ML techniques show promise for downscaling coarse simulations. The work was supported by the US Department of Energy. It's not quite the last day of the project, but it's pretty close to the last day of the project. I have to provide our final report by the end of October. And so just to provide a little bit about some opportunities to work at PNNL, and I mean, of course, I'm biased, but I recognize that there are other national laboratories as well. And there are a couple different ways. There's the Office of Science Graduate Student Research, SCGSR, that provides supplemental awards to outstanding US graduate students. So this is an opportunity to spend time at your home institution and then come and work with a mentor at the National Laboratory. I believe that QR code will take you to the website associated with that. And then at PNNL, we also have a website where we have positions listed. These include internships, postmasters, postdocs, and opportunities for staff positions. So I just throw that up there. Feel free to check it out. If you have questions, don't hesitate to reach out. PNNL fortunately has very intuitive email addresses. They are hard to find online, but it pretty much is firstname.lastname@pnnl.gov. And so with that, I will wrap up and take any questions.
This is wonderful. And we saw throughout this very comprehensive research program, going from geoscience to engineering, okay, and measurements, computer simulations, and machine learning, okay, all aspects. Okay, yeah. So now the floor is open for questions.
Really amazing work. So the simulations with the pitching turbines, the pitching was imposed, right?
Based on the wave field. So a wave field was specified.
But was the pitching calculated from the wave field and the wind?
Mm-hmm.
And so under what kinds of conditions cause such, like the ones where they're in phase or out of phase, or, is it typical? Is there some way to summarize?
Yeah, and I wish let's see if I can get back to. I was looking to see if I could go back to the equation, right? So this theta equation is the equation that's actually used to determine the pitching within this particular case. And here, the wave speed is around 11.5 meters per second. Wave period is 7.33 seconds. The wave amplitude is 3, and that led to, I believe, the wave length of about 84 meters.
So the pitching is only determined by the waves. It has nothing to do with the wind?
Right.
Oh.
There is no inertia in the turbine system platform.
I don't believe in this case that.
Pure kinematic.
Right, and really the idea here is that we could generate this time series of wind relative to the turbine that then could be implemented in control strategies.
Right, but the distribution of mass in the turbine is quite important.
Right.
Because the system will have its own nominal frequency. Here we assume it's
Right,
exists.
right. You could view it as the first cut, right? If we'd have the actual funding for the rest of the project, we would dive into it in more detail, right?
Questions?
Hi, wonderful talk. So when I see your turbulence for the opposite case and for the line case, I do expect we have less power in the opposite case because we have more dissipation, especially near the water surface. But your results showing the opposite case. The opposite case has the higher power output. So what do you think about that reason?
Yeah, I think what's largely happening is that in the opposite case, there's actually enhanced turbulence. And so the wake is actually dissipated faster. I think is primarily the physical mechanism that's driving it.
Other questions?
Thanks for a nice talk, Larry. I was just curious about you showed this in phase, out of phase, and have you measured the wake width changes under different phase conditions?
That I don't believe they have, but that would be an interesting thing to look at to understand.
Yeah, the reason I ask this is because we have seen some kind of wake contraction behavior on our turbine, and we believe under certain cases it may be associated with flow structure interaction. In your case, you have imposed structure deformation. I was curious that might be, there may be similar phenomena occurs in that particular case. The second question, I think you showed the low-level jets, and have you looked at the veering phenomenon in the offshore conditions? I guess probably not. But
Not in any extensive detail, but that is important, and I think it's something that when we just look at things like the jet statistics, like I showed, that it's easy to lose track. That there's the wind speed shear, or the changes in wind speed with height, but also if the wind is changing direction, which would change the stress on the system.
Yeah. So regarding the data of low-level jets, do you have this data publicly available somewhere?
Yeah, it should all be, and I can point you to it, but the Wind Energy Technology Office maintains a data archive, and I believe that all that data is there.
Yeah. All right, thank you very much.
Ash?
Thank you for that nice talk. Yeah, I had a question regarding the wall modeling. You mentioned that the the flow of the waves is assumed like an ideal flow. So how valid is the assumption of the ideal flow of the waves?
That would be a great question for Charles. But I think it highlights, right, that some of I mean, because we had simplifying assumptions related to the details of the wind turbine, but there's also some simplifying assumptions related to how we assume the wave field interacts. And then, of course, in reality, right, the wave field is very complicated. And so it's not clear that this would necessarily be as accurate in that case.
And can this wall model be extended to like general like broadband wave scenarios, not only monochromatic?
I would have to talk with Charles. I honestly don't know off the top of my head.
Right. Nope.
Hello, a nice talk, Dr. Monk. So I had a question regarding the thermal stratification. So I think this is for the neutral boundary layer. So have you considered the effects of the stable and the unstable? Like what would be the effects on the power output or on?
We have, honestly, we have not, right? We've not had time to do that. It's taken a while to get to this point, but certainly it's important because one of the things that I think is important to note is that neutral conditions actually happen relatively infrequently, right? That more often the atmosphere is either statically or unstatically, or statically stable or unstatically stable. So it is important to extend it. And I think that particularly in the unstable conditions, I would anticipate that the wakes would dissipate faster, right? And in a stable condition that the wakes could actually propagate much, much further, particularly in these maritime kind of environments.
Right. Professor Dan Griffin.
Thanks. I had a question not about the fascinating science, but more about its destination. I'm curious about the public-private partnership,
Right.
and where this work is headed. This is publicly funded. It's really cool discovery-based science, and it's also true. It's, I think, set up to serve an industry that is largely private, the wind industry. And meanwhile, the wind industry has their own kind of shops doing amazing work.
Right.
And so, given your perspective and position, can you just talk about the flow of information exchange across the public-private kind of partnership?
Yeah, I can talk a little bit about that. Not so much in the context of this project, because this is, I think, well ahead of where much of industry is. Where I have seen us, I mean, we interact typically with industry, or I personally have interacted in industry in a couple of different ways. One is as we think about how we design the meteorological models, working with them to find out, what are you doing? Right? Where do you actually see, what do you think is driving the uncertainty in your simulations? Where should we be putting our attention? And they've been very helpful in that regard, and I think that's a valuable. Sometimes basically pro bono, and I see them at a conference and we talk about it, I'm thinking of using this representation or this representation of the physics, which is better. We've had some where there's more overt kind of collaboration, where there's actually some funding between, we're providing some support. And in those cases, we've done things like looking at the base physical model. One of their secret sauces, the people that provide forecasts for the industry, is machine learning on top of that. And so we want to make sure that if we improve the physical model, that we still see an improvement after their secret sauce, right? Because maybe we have biases that their machine learning is getting rid of. And we found out that that was not the case, right? So this one was focused more on solar forecasting, but we saw improvements with our physical improvements to the model, and then retuning or retraining their machine learning application. There are also interactions with the companies that design hardware. The lab I work at tends not to do that. NREL does more of that kind of thing. And then there's more contractual mechanisms that allow a national lab employee to work with them in a way that's not as open to the public. Is that?
Any other more questions? If not, well, I have a question at the end. So yeah, so this acronym, okay, the last two words, CC, changing climate. Like
Yes.
this. And I'm wondering if you can comment more about that. At the end, you showed the things like atmospheric rivers, like
Right.
So it's like how to understand that.
Right. So the way the call was written, I thought I was being very responsive because the call was about floating wind, so I had to have floating wind in it. And really, the approach we wanted to take in ours is that we want to make sure that if we improve the physical model, that we still see an improvement after their secret sauce, right? Because maybe we have biases that their machine learning is getting rid of. And we found out that that was not the case, right? So this one was focused more on solar forecasting, but we saw improvements with our physical improvements to the model, and then retuning or retraining their machine learning application. There are also interactions with the companies that design hardware. The lab I work at tends not to do that. NREL does more of that. And so we want to make sure that if we improve the physical model, that we still see an improvement after their secret sauce, right? Because maybe we have biases that their machine learning is getting rid of. we need to understand how the operating environment is going to change over the lifetime of the wind turbines, which is maybe on the order of 20 years, and changes to the grid, which have a much longer time constant than that. So we really needed to look at what operating conditions are today and what they will be on into the future. So that was really why we were linking with E3SM, was we wanted to be able to look at how the conditions might be different, how the wave fields might be different, how the frequency of extreme events might be different in a future climate, particularly in these kind of environments where the design criteria, where they're in such a harsh environment, that we really felt like we needed to have a good feel on what the design criteria would be. And now you can guess how out of favor that is with the current administration.
All right. Okay. Well, okay. I just want to, at the end, mention something more about what Dr. Berg showed. So on one of the slides, he showed, projects, and one of them projects is Awaken. Then I realized immediately Professor Holmes, Gerald Holmes, former student Alisa Abraham, she has been very active in that project for that. And the SAFOR students, have a tradition of working for national labs. And for example, Professor Michele Guala's former students, like Mirko and now Gion, so they are at Oak Ridge, for example, National Lab, very successful. And also, other professor like Professor John Gallagher, and he has a former student, Adam Witt, and I had the fortune to be his co-advisor. And then, when I went to DOE to talk to program manager, then program manager said to me, on this problem, I suggest you to talk to Oak Ridge National Lab, Adam Witt. Then I look at the back and said, I was Adam's co-advisor. Okay, so, SAFOR students working at the national lab, they make us very proud. But I don't recall, anyone from SAFOR working at the PNNL. And so now, if we are interested in DOE National Lab, and that actually is a very good career path. As I used a few examples to show. That's what? Correct here? Yeah. Okay. Yeah. Okay. Yeah. Okay. Yeah. Correct. I think he's not in the room. Yeah. Anyway. So if you are interested, hey, I brought the division director here, and he left his email address on the last page of the slides. And I'm sure if you applied for PNL job or in his division, the one you are going to interview with one level or two levels below Dr. Berg, and you are talking to their boss or boss's boss now. Okay? Yeah. So with that, I really appreciate Dr. Berg gave us this time. And I met him at the AGU4 meeting last December. And then I said, well, I got to invite him to come to SAFOR. The only thing is whether he will have the time. And he found the time for us. So with that, let's give Dr. Berg another round of applause.
Well, thank you. It's been a lot of fun, and seeing the facility. And I also was careful to pick a time not too deep into the fall, when the weather might still be comfortable. So thank you very much for your time.